All right, let's talk about oxidation numbers and oxidation reduction reactions. Here's some basic rules. The oxidation number of any free uncombined element is 0. That is your just free elements. We're going to treat them as 0. Oxidation number of any simple monoatomic ion is the charge on the ion. We got that from our ionic nomenclature, so that's not really new. In the formula of any compound, the sum of the oxidation numbers of all the elements in the compound is 0. We're going to use that to determine, to have something to set it equal to get a interaction. That's how we've determined the formula of the ionic compounds. If it's a polyatomic ion, it's going to add up to charge on the ion. We're going to need some reference elements. And so fluorine has an oxidation number of -1. Hydrogen usually has an oxidation number of +1 unless it's in a metal hydride like lithium or barium hydride, then it's -1. And we got that from our ionic chapter as well. Oxygen is usually -2 with some notable exceptions. In peroxides, oxygen has an oxidation number of -1, like hydrogen peroxide, and in OF2, oxygen has an oxidation number of +2, and usually write the plus with the number. If there's a conflict, as in the exceptions, you're going to apply rule 5, 6, and 7 and apply the lower number. You're going to apply the lower numbered rule and ignore the conflicting rule. So we're going to determine the oxidation numbers of each of these elements or compounds and see what their oxidation numbers are in each case. And there are a couple of exceptions in there. So here are our substances we wanted to determine the oxidation numbers of. Nitrogen's pretty easy. That's a free element, so we know the oxidation number is 0 just by applying our first rule. So we're going to look at B, sodium nitrate. We know sodium is ionic, and so it's going to have its oxidation number is going to be the charge, so that's going to be a 1. Our nitrogen, we don't know, so we're going to call that X, and because that's what we're going to have to solve for. Oxygen we got a rule for is -2. So that's -2, that's +1, and then X. So we can set that equal to 0 because the compound is neutral, plus X plus 3 times a -2 equals 0. And so we can see that ends up being -6. So we get X minus 5, because we add that 1, equals 0. And I'm going to go ahead and cross these zeros so we don't confuse them with O for oxygen. So X is equal to +5. So the oxidation state on the nitrogen and the nitrate is +5. Now if we got SO3, we again can say the oxygen's -2. That's going to be your X. So then we're going to say X plus 3 times a -2. But this time we're going to set it equal to -2 because that's the charge on the substance. So we're going to get X minus 6 is equal to -2. So then X is going to be equal to a +4. Now, the last two are two of those exceptions, hydrogen peroxide. We can apply the +1, but you can see rather quickly that if I apply the -2 for oxygen, it's not going to add up to be 0 like it's supposed to. So we'll go ahead and make it an X. And so it's going to be 2 times a +1 plus 2x equals 0. So then 2x equals -2, so x is going to equal -1. And then that's just what the rule said it would be. Oxygens in a peroxide are -1. Now, again, in E, fluorine is -1 according to rule, but oxygen's negative. That's even more obvious. That's not going to work, so we're going to make that the x and solve for it. So we're going to say x plus 2 times the -1 equals 0. So x is equal to +2, which is what we said in the exception to the rules. And so those are some oxidation numbers of some elements and compounds. So what happens if the oxidation number changes over the course of a reaction? Oxidation is an increase in the oxidation number corresponds to a loss of electrons. That is, it's becoming less negative or more positive in terms of the charge or the oxidation number. For example, sodium, metal going to sodium +1 and losing an electron is an oxidation. A reduction is a decrease in the oxidation number, and it corresponds to the gain of electrons. So you just have to remember reduction reduces the oxidation number. So sulfur plus 2 electrons forming sulfur -2 or sulfide is a reduction. So it's going to become less positive or more negative if it's being reduced. We can kind of use the mnemonic device oil rig. Oxidation is the loss of electrons, and reduction is the gain of electrons. I like this number line representation of oxidation numbers. That is, oxidation is going to be movement from left to right. That is getting less negative or more positive. Reduction is movement from right to left on the line, meaning that it's getting less positive or more negative. And a lot of times it's easier to remember it that way than a lot of the other mnemonic devices people try to use. So then we got oxidizing agents. Those are substances that oxidize some other substance. They're going to contain atoms that are reduced and therefore gain electrons. So the oxidizing agent is the substance that is reduced. The reducing agents cause the reduction of something else. They contain atoms that are oxidized and lose electrons. You hear about oxidizing agents a little bit more than reducing agents. Reducing agents tend to be highly water reactive in many cases. Oxidizing agents are things like oxygen gas or anything that's going to help the burn rate of something else, or rust metal or things like that are good oxidizing agents. So let's look at the following reaction. Potassium permanganate reacting with HCl's and 5 FeCl2s are going to produce manganese chloride, 5 FeCl3s, 4 waters, 1 potassium chloride. That's a balanced redox reaction. We won't focus on balancing the more complex ones in this course, but we wanted to look at the oxidation numbers and be able to do them quickly. So we're going to get the oxidation number of each element in the reaction, find out what's being oxidized and what's being reduced, and how many electrons are lost or gained respectively in the oxidation and the reduction. Okay, this is my oxidation and reduction reaction, or sometimes they call it redox reaction for short. That means the oxidation numbers are changing. A lot of these we can get by our ionic rules, and then we can get the other ones. So since these are all ionic compounds, potassium is +1 because it's in group 1A. We had a rule for the oxygen, -2. I don't know this one, so I'm going to have to come back to it. This is +1 and -1. This is +2 and -1. This is +2 and -1. I'm just following the ionic nomenclature. That's going to be +3 and -1. Water's +1, -2, based on our rules, and then +1, -1. So the only thing I couldn't get based on the rules was this manganese and the permanganate. So let's get that. So that's going to be 1 plus x plus 4 times the -2 equals 0. So that's going to be x minus 7 is equal to 0. And so x is going to be equal to +7. So that x there is +7. Now I can see what's changing. I could see that the iron was in fact changing, and in fact the manganese changes, right? So are they oxidations or reductions? If we go back to the iron, we're going from +2 to +3. So that is an oxidation, which must mean that this has to be a reduction, because you can't have an oxidation without a reduction. The what one loses, the other one gains. And so I have to have a net transfer of electrons. So that's my reduction, that's my oxidation. Let's verify that though. +7 to +2, yeah, that's a reduction because I'm getting less positive. How many electrons? That's the only thing left. This was a total of 5 electrons involved in the reduction for each manganese that's reduced. Now the oxidation was only 1 electron per iron, but you notice there's a 5 coefficient there, so times 5, there's 5 total electrons transferred. So there's 5 electrons lost, 5 electrons gained, which means I do have a balanced redox reaction.